Okay. All right. So good morning, everyone. So today I'm going to talk about this topic of cross validation, and this uh, now chances are if you are doing a machine learning project, which most of you are doing, then you have already done some sort of cross validation, or you may be asked to do that. Um, So it is important to understand at a high level and in a deeper level as well, both levels, what cross validation is. Many of you, as I said, may already know about it, may have already read about it in your courses, but let's look at it again and see if our understanding improves or not. Okay, so this is your ideal world. So on your left side is your huge amount of data, and on the right side is your test data. So some of the terms that I will use today may be different from the terms that you have read on blogs and other places, right? And and we'll have your questions reserved after the presentation. Okay, so if you have any questions, just note it down, and then we'll have this Q&A after this talk. So this is the ideal world where you have lots and lots of data, and then this blue thing is the wall, and outside the wall is this test data that we never have access to. Okay, so a good example is driverless cars, for example. So you train your cars on huge amounts of data from different cities, and now you're going to let's say Kingston or Ottawa, and you want to test, and you have never seen how the roads of Kingston, for example, looks like, right? This is a real world kind of situation. Sorry, an ideal world situation. Now, in a real world, what happens is that the data is very limited. Most of the time, you're not given any test set as such. You just have one chunk of data. Now that could be 100 samples, that could be 1,000 samples, that could be 100,000 samples, right? And Reza actually recently took part in this competition, and he could attest to a good taste of what a test set looks like, because he took part in this competition and he never got access to the test set. So he was only given some you know uh, some data to work on, and that's what you just build your model on, right? So how do I train a simple classifier, or how do I train a model? So what I do is, the simple way is, you have this data and then you split it into two using some combination, 70-30, 80-20, 90-10, whatever you come up with. So you split the data into two parts. You train on the training part, and then you test on the test part, and maybe you get, let's say, some performance number. So is this a good approach? No. And why it is not a good approach? Because this is highly unreliable. And what do I mean by unreliable? Because you are only making one split of the data. Now that split could be a very good split. It could be a very bad split. So you may end up having very good results on your test set. You may end up having very bad results on your test set, right? This is just one split. So it is really hard to generalize the performance of the classifiers and of the classifier that you're training on, right? And then the estimate of error or performance you get will be very unreliable, will be, it's really hard to trust this kind of classifier, because you have just made an arbitrary kind of partition in the data, right? So how can we improve that? Now to do that, we do cross validation. And the main purpose of cross validation is to reduce the estimation bias. Like, whatever errors you want to estimate, you just want to build you want to build a classifier on different partitions of the data. So in the end, you are able to reduce the bias. Now, there are two major ways of doing cross-validation. One is k-fold cross-validation, and the other one is leave one out cross-validation. And I'll go into both of them in a little bit detail. Okay, so imagine you have 100 points. So I'm talking about k-fold cross-validation. Now, k in this case is arbitrary. It could be 2, it could be 5, it could be 10, it could be more than that as well, 20, 100, whatever. So let's imagine just this is a k, okay? So let's say we have 100 samples. So in a k-fold cross-validation, so let's say I'm doing a 10-fold cross-validation. What I do is I split the data into two parts, like I showed you in the previous slide, but there I only do one split. Here I do 10 splits in such a way that 90% of the data is used for training and 10% is for testing. So that's why you see these two bars. So you have 1 to 90 in the training, and these numbers are the object numbers. And then from 91 to 100 are your tests. So this is one split. And then P is some performance metric that you compute from it. It could be an accuracy, it could be whatever. Then you do the second fold, where you take the next 90%. So from 11 to 200, and then 1 to 10 will be your testing set. And then third fold, and so on and so forth. And then you do your 10 folds, and you get performance metric for every every fold, and then you do some averaging. Okay, so you report like an average kind of metric across different fold, and you report mean and standard deviation and other kind of performance metrics. So this is a simple k-fold cross validation. Now, why? I mean, what is the extension of k-fold cross validation? And I think the real importance comes into picture when we have more than one classifier. So if you're doing all of this on one classifier, it is okay. I mean, this is a neat way and a nice way of evaluating a classifier. But then if, let's say, there are two classifiers and I ask you which one is better, right? So the right way to compare is that you pass the same training fold to both the classifiers. So let's say if we are looking at fold 1, then the classifier 1 and classifier 2 should see the same training fold and should be tested on the same test fold. Should see the same training fold and should be tested on the same test fold. It is very important, otherwise your classifier, your comparisons will not be fair. For fair comparisons, the training and testing part for different classifiers should be the same, because many of you will be testing your algorithms on different classifiers, right? Nobody is working on one classifier. Now, different classifiers can be different variants of the same classifier as well. So if so, for example, you're using autoencoder, so it could be autoencoders with different configurations. It could be autoencoders with different number of layers, activation functions, different hyperparameters. Even if there is a slight change in one type of classifier, it is a different classifier, right? So to compare those classifiers, and you can have heterogeneous classifiers. So you can have SVM and random forest and CNN. So these are different families of classifiers. So these, or you can have this, classifier from the same family. It does not matter. Even if there is one parameter is different, they are different classifiers. And when you compare these different classifiers, the training set and the test set should be the same. So this is what I summarize here, that you go into each fold. So for each fold, train these classifiers, C1 to Cn, whatever classifiers you have on the train partition I, and then test the same classifiers on the test partition I, and then you can obtain the corresponding matrix, whatever M1, M2, Mn corresponding to these classifiers, and then report the average performance matrix. Now, I'm not going into the details of how to compare the performance of the classifiers. That is a separate discussion. Normally, I mean, it depends upon in which community you operate. If you are trying to publish your papers in machine learning community, then they may ask for statistical testing. Because let's say if you are getting 0.85 and then performance with one classifier and 0.86 from from another classifier. So can you really say that classifier 2 is better than classifier 1? Because 0.86 is very close to 0.85, right? It could be just due to some random noise or some minor changes, so a better way to deal with that is to do statistical testing. Now, I'm not going into that today, but if there's a need, we can have a separate, talk about that. But in hardcore machine learning, papers, you would have to do statistical testing, and I've done that a lot in our papers, and there are specific ways to do it. Most of the time in the deep learning community, especially in the computer vision side, they don't do that, which I really don't like. But we can talk about that. But statistical testing is also important, because if you are saying, oh, I'm getting 0.89 and somebody got 0.88, it does not mean that you're doing good. It could be just an artifact, just the presence of noise or something, so it is very important to rigorously, test the power of your classifier as well, through statistical means as well. So we can have that discussion at some other point. Okay, so the next is this leave one out cross validation, which in a way is I mean, k-fold cross validation is a special case of leave one out cross validation. In leave one out cross validation, as the name suggests, you leave one sample or one data object for testing, and then you train on the rest. So for example, if I have 10 data objects, so what I do is I train on the first 9 and then test on the 10th in my first fold, and then in the second fold I train on the next 9th and then test on the next test, and so on and so forth. Now, as you can see that I have 10 objects, then I had to train 10 classifiers. If I have 100 objects, then I have to train 100 classifiers. The good thing is that in every fold, your training data is more, because you're just testing on one object, right? But at this, so which is good that your classifier has access to more data, because more data is good to build generalizable classifiers. But the problem is that if you have millions of data points, then you will end up training millions of classifiers. And if one classifier is taking, let's say if you're doing a deep learning kind of approach, if one classifier is taking 1 day, it means that you would need 1 million days to just test this technique out, which is insane. I think nobody lives to that large amount of time, right? So the problem with this approach is that it is computationally intensive for large data set. And as I said, the number of classifiers that you have to train will be too many, right? So, but for a smaller data set, this is still a viable approach, and one can do that. There's no harm in doing that. But even if for a small data set, it will be computationally intensive. Now, another variant of leave one out cross validation is leave one person out. Most of us who work in health kind of approach, in health type of domain, we may have data from different persons. So for example, activity recognition or whatever, in our group, we worked on agitation detection and fall detection and things like that. So in all these applications, you would collect data from different individuals. Now in this example, I show, let's say we have data from five subjects or 5 participants, right? Now, as you can see, the size of these of each of these boxes is different, which means that you may end up collecting different amount of data from different people, right? I mean, depending upon your protocol, you may want to collect equal amount of data, but in a real world setting, that may be very hard to achieve. Sometimes your sensors may fail. Sometimes a person is not, compliant. There may be some other issues, hardware, software issues, data transfer issues. So in a real world, it's really, really hard to get equal amount of data from all the participants in your study. So if let's say, so let's say you have these 5 participants in this example, and everybody, you got different amount of data. Now I want to build a generalizable classifier, and I want to do, cross validation on this. So one approach is we can actually do the way that I told you, cross validation, that you combine the data from all of the people, right? And then, so S1 plus S2 plus S3 plus S4 plus S5, and then you can shuffle that data and then do the tenfold cross validation. That is one way of doing it. But we normally do leave one person out cross validation. In this approach, the data from n-1 subjects are combined together and tested on the nth subject. The advantage of doing this approach is, using this strategy is that the classifier that you build this way will be more generalizable on an unseen person. So depending upon your goal, what do you want to achieve? Most of the time, what we want to achieve is that whatever technique we are developing should work good on an unseen person, right? So let's say if I'm doing fault detection, so I want to train data, train my model on whatever thousands of people that I have data for, but when I want to deploy it, I want it to work well on that new person. And when you deploy it, then only you are actually testing. Here you're not testing. And this is one of the things that I want to make sure, and I want to repeat, that in cross validation, you're actually faking that you have a test data. You never have access to the test data. I mean, there's no concept of test data because you are not deploying your classifier, right? The real testing, like the example that I gave you about this driverless cars, the real testing is when you actually deploy your algorithm or your classifier. But here we are not doing that. If let's say in one of our study, if let's say fall detection study or agitation study, if we deploy that classifier or algorithm in somebody's home or in some nursing home or wherever, let's say this driverless car example, if I drive that car in a city that has never seen, that is the real testing. But most of the time, the data that you have, you're not deploying it, so you're not actually testing in its true sense. So cross validation in another way, loosely, you are actually faking that you have a test data. So that is why you want to change the scenarios, because you actually don't know how it will work in the real world, right? How it will work in an actual situation. So that is why you are trying to build a classifier on different scenarios. So in the sleep one out scenario, like as I said, we could also do a k-fold cross validation. We combine all the data and split data into whatever, let's say 10 folds, and we could do that. But that you will still do that, but that classifier will not give you a good sense of how it will work on a new page, on a new person. But if you do a leave one person out, then it will give you a good sense of how it will work for a new person. So let's say in this case, I'm just doing a 5-fold cross validation. So I combine data from 4 people, S1 to S4, and then test it on S5. And similarly, S2, S3, S4, S5, and then test it on S1. So these are my 5 folds. Now, if you see one interesting pattern, that in every fold, the training size is different and the testing size is also different. In the k-fold cross validation, we kind of make sure that the training set is 90% and the test set is 10%. Here, that restriction is not there. And I think you can make it out the difference. The difference is that in this situation, we are not enforcing that constraint. We are enforcing the constraint that we should have the same number of persons in the training set. So we should have n minus one subjects, but the nth, and we test on nth, and each person may have different amount of data. So that is why the training size may vary, right? And the testing size may vary, but you're still doing this, but the principle is the same, that you're training on n minus one subjects and then testing on nth subject. And again, you can get these performance matrix, whatever you have, accuracy, uh, true positives, whatever, false positives, geometric mean, other kinds of matrices, and then take an average. And this will give you a good sense of how this might work for a new person when you deploy the system, right? So this is leave one person out. And okay. Now, one more variant, and maybe you already heard about that, stratified cross-validation. So what do I mean by stratified cross-validation? Until now, I only talk about splitting the data in terms of data objects. Like you have 100 data objects and you want to split it. But what if, and which is most likely the case, that the data has different classes. So for example, you have cats and dogs. So you have 100 cat sample and 100 dog sample, and you want to do a cross validation. So how are you going to split them? Should I, like, what should be my strategy? And to understand that, I'll give you an example. So let's say I have these two classes, A and B. A has 70 samples and 30, and B has 30 samples. So it's slightly imbalanced data, right? And I ask you to do cross validation on this data set. Good enough. So what you do, you combine A and B. A and B can be your cats and dogs. So you combine A and B, and now you have 100 samples in your data, right? Now what you want to do is you want to do a cross validation. So let's say we do a 10-fold cross validation. So I'm giving you a worst case scenario example. So in the worst case, it may happen that the train set that you create, it may have 60 samples from class A and 30 samples from class B, which is 90, and your train set should have 90, right? And in your test set, you have 10 samples from A and 0 samples from B, right? This can happen because if you're doing it randomly, then this can happen. This is a bad choice. Why? Because you would not know how your classifier works on classifier on this class B, right? So, and you will not be able to calculate some of the matrix that you want to calculate. So for example, if B is your class of interest, you would not know what is true positive rate. So this is a bad choice. So how, and this becomes very apparent when you have imbalanced classes, right? If you have balanced classes, so let's say if you had 50 samples of A and 50 samples of B, then just by random sampling, it would choose 50% from class A and 50% from class B into the training set, and it should not be a major problem. But the more imbalanced classes you have, the severe the situation would be. Like just imagine instead of 30, you have 10 samples of class B, then there are more chances that all of them would go into the training set and nothing will be there in the test set, right? So then we enforce this thing called stratified cross validation, that when we create these training samples, we make sure that they are equally distributed in the training and test set. So what I would do is, actually, I would recreate this fold one such that I have 90% of samples from A, so which is 63, 90% of samples from B, which is 27. And if you add them, they will still be 63 plus 27 is 90. And in the test set, I want to have 10% from class A, which is 7, and then 10% from class B, which is 3. So 7 plus 3 is 10. So the numbers still are the same, they add up, but they are distributed differently. Now, in this case, in the second case, you will never have that scenario where you have no samples from any of the classes, right? So this is very important, and a lot of these APIs that you use in Python and MATLAB and other, I think, languages, if you want to use, they have this option of a stratified, and it is really important to use stratified. Otherwise, I mean, you may also end up in an average case scenario. So this first scenario I gave you was the worst case scenario, and the second one is the best case scenario, which we must do. But you may end up with a average case scenario where if you're not doing stratified cross validation, that you may not end up with 0 samples in B, but then you may be having 1 or 5 and 7. So that would again be not a good approach, and your errors will have more bias. That is the problem. So you just want to be consistent across all the folds. So it is a good idea to stratify, especially if you have imbalanced classes. And most of these modern APIs and programming, they have this facility to do that. So you just choose some options, and then it would do stratified cross validation for you. So all the approaches that I talked about, whether it is K4, leave one out, leave one subject out, whatever, if you have multiple classes, make sure that they are well represented across different folds. So it's cross, right? This is the part, and my animation has gone bad here, so there's an arrow already. But I think the most part that I have seen many people get confused is this hyperparameter tuning part. And I want to spend a little bit time here and see if we can clarify some of your doubts. So let's say you have 100 samples. Again, we start with the same scenario, and let's say you have I'm doing 10-fold cross validation. You have 90% of your data in your training set, and 10% is the test set. Now you see a line there between train and test set. This line is actually to signify that you will not have access to the test set. And in the cross validation, previous slides, when I said test set, so whenever you hear the word test set, it means that that data is not accessible to you. And I think the root cause of problem is that you have access to your data, and then you get confused that I already have the data, so why I'm pretending that I don't have the data. I think that is the root cause. Basically, the test set is something that you have not seen, that you don't know nothing about. But the problem is you already have your data in front of you. So in a way, you're kind of pretending that I don't know what the test set is. So whenever you create a test set in your data, just forget about it. That's the data that you have never seen. I mean, at least you have to kind of, pretend. So when I create training and test set, so this 10% data is kept aside and I know nothing about it. The only data that I have access to is this 90 samples. Now, let's say you are doing some neural network or SVM and random forest or whatever. So every classifier has certain parameters that you want to tune. So in a SVM, you have a soft margin parameter, what kind of kernel you want to choose. Similarly, in random forest, you may have like the depth of the trees and how many nodes you want to consider, split number of splits, things like that. In neural networks, there are so many hyperparameters, the number of layers and activation functions and optimizers and blah, blah, blah. So every classifier has its own parameters. How you would know which parameter works better. So there you do some hyperparameter tuning. Now, on the right side, this test set, you have not seen that, you don't know about it. The only thing is this 90% data that you have. So what we do is we then split this data into two parts. And sorry for the abuse of notation, but then this part is also called as training and validation. Now, on the right side of the screen, I don't know if I can, but okay, let me not annotate it. So just imagine on it, everything on the right side, you have no access, and everything on the left side is the thing that you can work on. So you split that into two parts, training and validation. Now, this is where a lot of confusion occurs. Many people call it as hold set or held out and whatever, different names. But in principle, uh, this is the name, but you can give it any name. But the important part is to understand that from a given data, you can create three partitions: training, validation, and testing. And validation is actually a part of your training data. So in this example, on the left side, we split the training data into two parts, training and validation. And actually you can do another round of k-fold cross-validation on the training data. So you can actually do this k-fold, cross-validation on your training data, and then you split this training data into, let's say this time I want to do threefold cross-validation. And this cross-validation doesn't have to be the same as your outer cross-validation, right? It can be a different number. It can be a threefold cross-validation. It can be a twofold cross-validation, five, whatever you want to choose. That does not matter in this context. So let's say if I'm doing a threefold cross-validation because I want to tune certain parameters. So let's say, let's take a simple case of SVM, and there are two parameters there. One is the soft margin parameter, and the second is just, let's say I'm just using one. I mean, let's say kernel, I don't want to tune. Let's say I'm fine with linear kernel. I just want to tune the soft margin. So I have one parameter there. So I split my training data into train and validation, and I do a threefold cross validation. So I train on the 2/3 of this data, which is my training sample, and 1/3 is the validation. And then I switch these partitions, like as I said before, the next 2/3 is my training, and then the next 1/3 is my validation. And I repeat it, let's say 3 times, and then find the the average performance metrics. And I do this, and I do the same for all different values of the parameters that I want to tune, and then whichever parameter is giving me the best or the highest number of performance metric, I choose that. So this part is called inner cross validation. Okay. And we are into fold 1. So within one fold, we are doing another round of cross validation to tune the hyperparameters. And we find the best parameters. And a good strategy is that when you find the best parameters, so let's say you found out that some c equals to 0.01 is the right parameter, then you retrain on the full training set. So your entire from 1 to 90, you combine training and validation set, and then you retrain on that best parameter, right? So first you split into train and validation. You do whatever k-fold or any technique you're doing, and find the best parameter, and then you retrain on your entire training set, and then you find the performance metric on the test set. So this performance metric on the test set will be based on the tune parameters. Then and this is called the outer cross validation. And I just showed you one snapshot of the fold 1. Then you do cross validation for fold 2, fold 3, fold 4, and every fold can have its own internal cross validation steps. Now the question is that for every steps we may get different parameters. We may end up finding different parameters for different folds of this cross validation, and it is okay. It is fine, because every training sample is a different visualization of the world. And in a cross-validation, this is what you want to do is you want to show different types of world to the classifier so that it can generalize better on an unseen sort of scenario, right? Okay, I hope this step is clear and we can touch upon this in the Q&A after this. And okay, so this is a question that I think based on some of the discussions, I think it is important to understand, and many of you may already know, what does a classifier actually output? You know, we're talking about all these fancy classifiers and all these methodologies, but in principle, what does a classifier give to me, numerically speaking? Now, if you're thinking that a classifier gives you a label, then you're thinking wrong. Classifier doesn't give you labels. Classifier can give you one of these things. It can either give you a probability, for example, your knife-based classifiers, feed-forward neural networks, convolution neural networks. These type of classifiers, they give you some probability between 0 and 1. Other classifiers like SVM, they give you some confidence type of thing. Basically, the margin, like how far it is, how far this is from the hyperplane that separates the positive and negative, right? Or a score like a k nearest neighbor. So even if you are working on neural networks, it is important to understand these basic classifiers. And I will highly recommend all of you to take a book, some standard machine learning book, go back and read about these classifiers. It is really, really important, even if you're working on these fancy classifiers. So KNN, what does KNN gives us? KNN gives us a distance. I can use that distance. So based on that distance, you take a decision whether it belongs to class 1 or class 2 or whichever class. Or people, I mean, some of you may be using autoencoders. So autoencoders gives you a reconstructions error. So no classifier or even decision trees. So no classifier gives you a label. It only gives you some probability, some confidence, some score, something like some numerical number. And based on that number, we decide whether it belongs to class 1 or class 2 or this or that. And that is, and once you decide that it belongs to class 1 or class 2, then you create a confusion matrix. And from the confusion matrix, you calculate these different matrices like accuracy, true positive rate, false positive rate, and so on. But it is very important to know that one confusion matrix only corresponds to one operating point. And what I mean by that, so let's say your classifier is giving a probability. Now, naive Bayes is a special case because in naive Bayes, if the probabilities that you get are actually normalized. So if you have two classes, then it says P1 over P1 plus P2. So by default, the threshold is 0.5. If you have 3 classes, by default, the threshold is 0.33. If you have 4 classes, by default, the threshold is 0.5, 0.25, right? But in other classifiers, there's no default threshold. Like at what point you would say that an object belongs to class 1 or class 2. So normally, we take a decision based on some knowledge or domain knowledge, and normally we say, okay, anything if it shows more than 0.5, or if it is giving me 2 scores. So let's say KNN example, if it is giving me 2 distances, like let's say 1.2 and then 1.3, then maybe 1.1 is more closer, so maybe it belongs to class 1, for example, right? But so what I'm trying to say here is that I mean, the choice of threshold is not clear. Normally, by default, we take the like 0.5 type of threshold, and then you get a confusion matrix. But confusion matrix is just, corresponds to one threshold. What if I want my classifier to be more sensitive? What if I allow more false positives? For example, in a fall detection kind of application, I'm okay if there are more false positives, for example, because I know that saving the life is more important. So I can allow 10% false positive. But maybe there are some application where you would say no, I don't want any false positive, and no, I want it to reduce. But then so you can actually change this threshold. It doesn't have to be 0.5. It could be 0.8. It could be low. It could be high. And one of the things that I actually did not mention earlier was that you want, when you're doing classification, you're trying to actually reduce this classification error or misclassification cost. Most of the time when we develop these classifiers, we assume that both the classes have the same cost, or both the errors, the false positive and the false negative are have equal cost, which is not true in most of the applications, real world applications. So for example, in this fall detection application, false positives means that you're showing these false alarms when there was not when there was no actual fall. This is a nuisance, this is an error, but it is okay, but like when we say misalarm, the misalarm is that somebody somebody falls, but your classifier is not able to detect it. Now this is a serious error because a person can die, right? So these are like very difficult questions, like, so what is the cost of a human life, or what is the cost of a false alarm, right? You cannot equate, and you cannot say that both of them are the same. They are different. And most of the classifiers that you're building, um, you don't use the notion of cost, and cost is an important thing that we have to consider. I'm not saying that you do it in your application, but it is something that you should think about, and feel free to talk to me about it. We may or we may not need in your particular application, but cost is something that is important to at least think about in whatever application you're working on. So by changing the different cost, or by changing the threshold, so my threshold is actually dependent on the cost. And by changing these threshold, I can come up with different confusion matrices. That's what I wanted to say. So so whenever you see a confusion matrix, or accuracy, or true positive, or false positive rate, this corresponds to one threshold, and there can be multiple thresholds. There can be actually infinite number of thresholds. And that is why I asked you to read that paper on AUC and the ROC curve. And based on these thresholds, you can actually create this ROC curve. And I'm not going into the detail because I believe that all of you have read that paper. And please read these good papers, important papers that will improve your understanding of what exactly is going on. So I'm just going to quickly touch about this AUC thing. So AUC, area under the curve. So once you generate the ROC, then you can calculate the area under this curve. And AUC has a very nice probabilistic interpretation. And it says, so if let's say, so it is actually a probability, I'll just read it out. The classifier will rank a randomly chosen positive instance higher than a randomly chosen negative instance. So let's say you have two samples, positive and negative. And if your AUC is 0.8, it means that you're going to rank the positive sample with 80% with 80% chance or probability. So that's what AUC is. And when we do cross validation, like if you remember from the previous slides, I talk about performance matrix. And this paper, now that performance matrix can be your AUC. Now this paper that I asked you to read, it actually talks about two ways of combining AUC in a cross validation setup. One is the pooling and the other is averaging. Averaging is okay when you're doing accuracy and those kind of matrices. Averaging in AUC does not make sense because for every fold, you will get one ROC curve. If you're doing a 10-fold cross validation, you will get 10 ROC curves. So you cannot actually make an average ROC curve. You can, so at the best, what you can do is you can report these 10 AUC values. So that is one thing. I'm also not very comfortable in actually taking an average of AUCs, because taking the average of probabilities is not that straightforward. So if you want to do an averaging approach, that is not right. So instead of averaging, you can actually report 10 AUC for each fold. The other way is the pooling method, and this is what I want to talk about. And then afterwards, and after that, I'll stop, because in that paper they did not tell exactly how to do the pooling. So there's one right way of doing pooling of AUCs, and this is as follows. So for example, you're doing a 10-fold cross validation. I'm just taking the same example that I talked earlier. So you have 90% for training, test 10% for testing. And in this case, I'm calculating some score. Now that classifier, the classifier that I'm testing can be an SVM, can be an autoencoder, can be whatever, your neural networks classifiers. So for these 10 samples in the test set, I can get 10 scores, right? Or 10 probabilities. And then for the next fold, I'll get the next 10. So similarly, by the time I finish this 10-fold cross validation, um, I would have tested these 10 test set blocks, and each of them has here you you have 10 samples. So by the end by the end of it, you would have calculated 100 scores. Okay, so these are your test sorry, blocks. So you see on the right side, they start from 91, 92, 100, and then they end up at 81, 82, and then 90. So this is what it is. And for each of these test sample, I can get, I have already calculated these scores, so I have 100 scores. And for each of these test samples, normally you know their labels as well. Otherwise, how would you evaluate? So those are your labels. So let's say 0 and 1s, right? Now in Python, it's very easy, but it is also important to use the right function, or the right yeah, so in the sklearn.matrix, you have this ROC underscore curve function. There are other ROC functions as well, but I like this one because not only it has the capability of taking the labels and the scores, but you can tell which class is of your interest. So are you interested in evaluating on class 0 or class 1? So this is the POS label. There is another function in Python where you do not have to give any POS label. You just give Y true and Y score, and it guesses somehow that maybe your class of interest is 1 or 0, which I don't think is right most of the time. You can change depending upon, I may ask you to evaluate how it is doing on the fall class, or how may it is doing on the normal class, right? So you should have that flexibility. So that is why I like this function. In MATLAB also, you can specify which class of interest, which is your class of interest. So let's say in this example, I would just write these 3 lines of code, and matrix.roc underscore curve. So all your test labels and all the scores. And you have to pass the scores. You do not have to pass the labels or any other thing that you're calculating from the classifier. The scores, the probabilities, the confidence, whatever you're calculating, reconstruction error, distances, all of those things are the scores. So your first parameter is the test label. The second is the scores, and then you specify, in this case, I'm saying class 1 is of my interest. And then it will give you false positive rate, true positive rate, and all the different thresholds. You can actually plot it, and you can see your ROC curve, and you can use this matrix.auc function, and it will give you the AUC value. The advantage is that by doing this, actually, you will get one pooled AUC value. You will not get different values for different folds, rather than you're actually finding one pooled value for the entire data. So this is it. Another thing, and I think that we can have in the discussion, that do we need cross validation in deep learning? There's no straightforward answer. Many people just don't want to do cross validation because they think it is time consuming. Well, welcome to machine learning. It takes time to learn and to do experiments. So just have the patience. In certain cases, you may not have to do, because if your data is like really large, if you're operating on the order of millions of data, then most likely no. But if you have a medium-sized data, if you are operating in the range of hundreds or mid thousands, then yes, you would have to do it, and you need to have a very strong case if you don't want to do cross validation. And so with this, I want to stop, and thanks for listening.